So, ladies and gentlemen, welcome. So today we are going to talk about the simulation of reflections. And the first thing I would like to emphasize here is the difference between local illumination and the scene reflections in a reflecting object. And that is what we also see here in the two images. So if you look at the left, then we see the reflection of light at a surface. And so what we consider here, and we have discussed that in some of the previous lectures, we consider a single point light, a directional point light, which illuminates the object. And then at every surface point, we evaluate the local illumination model, for instance, the Phong illumination model, to determine how much light that comes from that single light source is reflected at the surface point. And now if you look at the right-hand side, then we also see reflections, but now the reflections are a little different. What we see now here in the right object is the reflection of the scene. So that means that in this case here on the right-hand side, we have to determine for every object point of the reflecting object, which is the point of the surrounding scene that reflects at that object point. So keep in mind that in both cases we talk about reflections. However, on the left-hand side, we only have to consider for every surface point one single other point, namely the light source position, to determine what is the illuminating light and how much of that light is reflecting back at the surface point. And on the right-hand side, for every point on the reflecting object, we have to consider which is the point in the surrounding that reflects at that point towards the viewer. Yeah, now how can we do scene reflections, or how can we simulate scene reflections using the rasterization-based rendering pipeline? So we have learned that when we use the rasterization-based rendering pipeline, then we essentially project the scene, the scene polygons onto the image plane. And we have looked in particular at how the projection transformation looks like that realizes this operation. So now, and what we usually do is that we define the camera position as the center of projection. And then, and this is the center of projection for all the scene parts, and then we can just realize this particular projection using one single projection transformation that is applied to all the scene geometry. Now, if you want to simulate scene reflections, as we do here in the image shown on the bottom right, then what we have to do from a conceptual point of view, we would first have to determine all the visible points of the scene, like the visible points of the reflecting object, the point here, the point here, the point here, the point here. So as we do if we just render the scene. But now what we also have to do is, we want to know which is the point of the surrounding that is projected onto these reddish points here and is then reflected towards the viewer. And what this means is in principle that what we have to do is for each of these reddish points, we would have to compute the reflection vector. These are the yellow vectors we see here, because the reflection vectors tells us from which reflection direction the incoming light will be projected towards the viewer. And this would then mean that for each of the reddish points, or for all points which are seen here of the reflecting object, we would have to determine the reflection vector, and then we would have to render the environment into or from that direction indicated by the reflection vector in order to find the point of the environment that reflects at that reddish point towards the viewer. And this would then mean that the scene has to be rendered from multiple views for each of the yellow reflection vectors, or for each of the reflection vectors at any of the points in which the environment is reflected. We would have to render the scene as seen from that view, with the yellow vectors being the viewing directions. And then we would have to determine the point that is seen exactly along that direction. And this would then be the point that is reflected towards the viewer. And that would mean that we have to perform multiple renderings along these indicated by the yellow vectors directions. And this would essentially require many rendering passes. So we could essentially do this by just looping over all the surface points of the reflecting object in that image here, then using the location of that surface point as the center of projection, using the yellow reflection vectors as the viewing directions, and then rendering the surrounding, and then taking what is seen exactly along that yellow direction. And this would then be the point that is reflected further to the viewer. And it's clear that this is, of course, far too costly in general. So we need to employ some other techniques, which, as we will see, do not simulate these reflections in an accurate way, but at least approximate them so that at the very end we obtain something that looks plausible. Yeah, and first of all, we want to now look at some specific reflecting objects. In particular, we want to now look at mirrors, at planar mirrors, and we want to see how we can compute the reflection at such a planar reflector. And we will see in particular that this becomes very simple because we can just define one so-called reflection matrix, which then allows us to compute the reflection at every point within the mirror surface. There are essentially two basic algorithms for simulating reflections at a planar mirror. The first one, and this will be the one we are going to address in more detail in this lecture, is that we can just flip the scene at the mirror wall or the mirror plane and then re-render through that mirror plane. Okay, we will see in detail how this looks. And the other technique, which results in exactly the same mirrored reflection, is that we could, instead of flipping the scene at the mirror plane, we could also flip the point of view through that mirror plane and render the texture and render the scene from this different position. And the resulting image can then be used as a texture that is mapped onto the mirror plane. And I think if we understand the first algorithm here, as I said, which is the one we are going to address in detail, then I think we will immediately also understand the second technique. So, let's look at planar reflections now. So we see such a situation here. So we have a wall, and keep in mind that here this wall is supposed to be opaque. So nothing when looking from this camera position here, which is behind that wall, should be visible. And then in that wall we assume that we have a mirror, meaning that in that mirror we now want to see the reflection of the scene. Yeah, and so now what we are going to do, we will flip the scene through the mirror plane, so onto the other side of that mirror plane, and then we will essentially re-render the scene, re-render the flipped scene, and this will then immediately give us the mirror reflection. That is exactly what we see here. For instance, if we follow one of the view rays here, which goes here, which arrives at the mirror, then what we would do, if we would simulate the mirror reflection by using a ray-based approach, for instance, then we would say, okay, we have a normal vector here, that is indicated by the black arrow. Then by using the normal vector, which gives the orientation of the mirror plane, and by using the direction of the incoming view ray, we can then immediately determine the reflection vector. And then if one could tell us what is the point that is seen along that reflection direction, the point here, then we know exactly which point of the scene reflects at that mirror point here towards the viewer. And we are done. And now we see that essentially the same can be obtained by saying, okay, we don't want to explicitly follow the reflection ray. Instead, what we do, we just flip the entire scene, which is comprised of the three objects here, to the other side of the mirror plane. And then we just render the flipped scene, that is indicated by the dashed view rays here, as usual. And the points we then see of the flipped scene, these are exactly the reflected points of the original scene. Yeah, and in order to do so, the first thing we need to do is then to find a reflection matrix, or the matrix realizing the reflection transformation, meaning the transformation that brings the object from the one side of the mirror plane to the other side. Yeah, and there's another thing we have to consider. If we then re-render the flipped scene, we have to restrict drawing of the flipped scenes to the pixels in which the mirror is seen. That is clear because, for instance, if we now flip the scene to the other side, and if we look in particular at this blue object here, and we now follow the view ray here, then it's clear that we would see the point here. However, because now that flipped object is hidden by the opaque wall, we have to make sure that only those objects of the flipped scene are maintained in the final rendering, which are seen through that mirror part, so to say. Okay, so, and there's another thing we have to consider, because if we flip the scene through the mirror plane, then objects which are initially hidden or occluded by the opaque wall will become visible. We see that in this particular situation here. So we have initially, in the initial scene, let us assume we have the three objects here and also the object here. And if we now flip the entire scene at the mirror plane, then we obtain the three flipped objects here. And this object here is now flipped to the other side. And now all of a sudden, that object which was before in the initial view, in the initial situation, which was hidden by that opaque part of the wall, is now coming to the front, so to say, with respect to the current camera position. And now that object would be rendered and would occlude other objects. And of course, that we have to take care of, that this situation does not happen, meaning that we have to do something against those objects which are, so to say, coming from behind the mirror plane now in front of the mirror plane. We have to somehow make sure that they do not affect the final rendering. Okay, let's first look at the reflection transformation we're going to apply. And I think deriving this reflection transformation is fairly simple. Let us assume we have a mirror plane here. We have a point here which we want to flip to the other side of that plane. Let us assume, and this we can assume, of course, we have an arbitrary other point which is in the mirror plane. And then we can immediately compute the location of the flip point, the point here, by just saying the following. First of all, we compute that d here, so the distance of that point to q to the mirror plane, which is just the scalar product between v and n, which is essentially this distance here, or this length here. Which can be just computed by taking the difference between q and p, and then computing the scalar product with the normal of that plane, which of course we also have. And then we can compute the projected or the reflected point. So by just saying, okay, so we take q, and now we move from q minus 2 times along n, or into the inverse direction of the normal, and we do a step of d every time, meaning that we have one step here along the inverse normal direction of length, which we have computed here, and then we do another step, and this brings us then to the reflected point. Okay. Yeah, so we can write that out. So here now we have the d here, the scalar product between the vector connecting p and q and the normal vector. So we can multiply out here with the Q and the P, separating the Q's and the P's. The P, and this then with K being the scalar product between P and N, this gives us then what we have here on the right hand side. Okay, so we can write that down now for each of the x, y, and z coordinate components for the reflected point Q. That is just the Q, x, y, and z. We do it component-wise, minus then 2 times the n, x, y, and z. Then comes the first bracket here. That is here just the scalar product between Q and N. That is here the scalar product component-wise. The scalar product, for between Q and N, with Qx times Nx plus Qy times Ny plus Qz times Nz, plus 2, and then again here the x component of N times K, and K we have said is just the scalar product between P and N. Okay, that gives us an equation for each of the x, y, and z components of the reflected point Q. We can then factor this out in order to factor out the Qx, the Qy, the Qz here. So we do that for all components, and this then can finally be written as a matrix vector product. So here we have the Qx, Qy, Qz, which we just factored out before. Here on the right hand side, we have the coordinate of the projected point Q. And here on the left hand side, we then have the mirror transformation matrix, or the matrix realizing the mirror transformation, an affine transformation. We see that we have translation components here, and we also have scalings, and we have some elements on the side diagonals. And this matrix is just built by taking the factors here and just plugging them into the right components in that 4x4 transformation matrix. Now you see what we have now. Now we have a transformation matrix, an affine transformation matrix, and if we apply that matrix to all the vertices in the scene, then all the vertices are flipped to the other side to the respective other side of the mirror plane. And that means that all we have to do is now, in order to realize that transformation, we have to take that affine transformation. We have to multiply that affine transformation with the modeling transformation, which we apply to all the objects. And then we have automatically realized flipping of the object vertices to the respective other side of the planar mirror surface. So now we have to address the two problems which we have looked at before. So the first is that the mirror is typically not an infinite plane, but only has a finite area. If we go back to the illustration where we showed that, if we look at the mirror here, then we see that that mirror here only takes or makes up a certain part of the entire mirror plane, and we see some other part here is just made of opaque material, so that everything behind is occluded. And that means that we now have to take care of that and render the scene, which is now flipped to the other side of the mirror, only into those pixels which are, so to say, covered by the mirror part of the plane, because for the other parts of the mirror plane, we don't want to have that property. They should just look as usual. We only want to show the reflected scene in those parts in which we see the mirror surface. And we can do this by using another buffer type, which is provided by the rasterization-based graphics pipeline. That's a so-called stencil buffer. And we will see that by using the stencil buffer, we can essentially restrict drawing of fragments into certain pixels. And we will then use that by doing the following. We will first render the mirror polygon, and wherever a fragment for that mirror polygon is rendered into a pixel, we will set a so-called stencil bit in the stencil buffer, and then in a second rendering pass we can restrict drawing of the flipped scene to only those pixels where the stencil bit has been set in that first part. So, and then there's another problem, no? As we have also said before, the reflected scene should not be seen through walls, no? Through these opaque parts of the mirror plane. We don't want to see any other object. And that means that if now an object was initially behind such an opaque wall and it is now flipped over to the other side of that wall and now becomes visible, then we should somehow exclude that object from rendering. And that can be done in a very simple way. What we will see, we just define a clip plane, and with that clip plane we simply discard those parts of the scene which are now, due to the flip, are in front of the mirror plane. So that's a very simple approach, and you can imagine that this can be done in a shader, where you just for every surface point or for every fragment, which are in fact surface points, you determine where is the location of that fragment point, either in a view space or in object space. And then you define a clip plane as a global shader parameter or variable, and then you can simply test the fragment position against the clip plane and exclude whatever is in front of the clip plane from rendering. So yeah, let's look at the first part of the mirror reflection simulation, where we want to restrict now rendering of the flipped scene to the pixels through which the mirror is seen. Now that is what we see here in this example. So you've seen we have a scene, and then we have a mirror polygon, which is the polygon here, or the two triangles making up that quadrilateral here. And now we only want to see the flipped scene in that polygon, because only there the mirror is defined. Yeah, how can we do this? As I've said, we can use what we call the stencil buffer. So the stencil buffer is an additional buffer which has the very same size as the color buffer and the depth buffer. And in that stencil buffer, we can now store for every pixel a bit mask. Let's assume that it's just a 1-bit mask which can be turned on or off. And in addition to that, we now have what we call the stencil test. So the stencil test is a test that is performed in addition to the depth test. We have already looked at the depth test. After the fragment shader stage, then comes the depth test, which tells which of the fragments is closer to the view plane than any other fragment that has been rendered before, and then only the closest fragment is kept. And now, in addition to that depth test, we also perform a stencil test, and the stencil test is here well illustrated or explained on the right. So first of all, as usual, we can tell whether we want to perform stencil testing or not. And then what is done is essentially that you compare the stencil buffer value. So whenever a fragment wants to be rendered into a certain pixel, then you can look up the stencil buffer value, which is stored in the stencil buffer at that location, and you can compare that stencil buffer value with a reference value which you specify. And depending on the outcome of that comparative test, you can then perform some action. So you can say, okay, either you discard the fragment, it should not be rendered, or you can say, according to that test, or depending on the outcome of that test, you let the stencil buffer content, the stencil buffer value, be modified. So you can calculate a new stencil value depending on that test. You can also include the result of the depth test in that calculation here, but not so much of interest in this particular example. So just keep in mind, we don't want to go into any more details here. Keep in mind that whenever a fragment wants to be rendered into a pixel, if you enable depth stencil testing, then at that pixel location, the stencil buffer is read, and then the value of that at that position can be compared against the reference value. And depending on the outcome of the test, you can then let the system perform certain operations. For instance, you can say, okay, depending on the outcome of that test, now change the stencil value at that pixel, and or for instance discard the fragment from rendering, or a couple of other operations as well. And how we use it here is very similar to the example which we give here. The typical use of the stencil buffer and the corresponding test. For instance, so what you for instance can do, you can initialize the stencil buffer with the so-called dissolve pattern, what we see here. So let us assume that the stencil buffer values are just bits which can be set on or off. So by giving them values of 0 or 1. And now let us assume by whatever technique you have initialized the stencil buffer with the values you see here in this dissolve pattern. Then what you can then do is you render, for instance, the red quadrilateral here. And we see the fragments that are affected when rendering that quadrilateral. And for instance, then what you could do is you could say I specify the stencil reference value to be equal to 0. And now I say, okay, the only where the stencil buffer, that one here, where the dissolve pattern is now only where the stencil buffer is equal to that specific reference value equal to 0, we want to let the fragments pass the test and then render these fragments into the pixel buffer. And that the following then happens. So for each of the fragments here, the 4 by 6 fragments here, we would then look at the stencil values in the stencil buffer, and only where these stencil values are equal to 0, we let the red fragments coming through. And then we render the green polygon, and we say, okay, we now change the reference value, the stencil reference value to 1, and we say the green fragment should only come through where the stencil value is equal to that reference value equal to 1. And then at the very end, we obtain the image here. So you see, the red fragments have only been rendered into the color buffer where the stencil value at the corresponding location were equal to 0, and the green fragments have only been rendered where the stencil values were equal to 1. So you see, this is a very typical application of the stencil buffer, simply to restrict drawing to the pixels by using a so-called dissolve pattern. And now the only thing we have to do in addition, now we have to make sure that we create a dissolve pattern that corresponds to the application we have in mind. Namely, we want to restrict drawing to only those fragments which are affected or which belong to the mirror surface. And therefore, what we are going to do now, we render that mirror surface, and wherever a fragment of that rendered mirror surface is created, we just let the stencil value increase. So more precisely, that brings us then to the mirror rendering algorithm. So in step A, we initialize the model view matrix, we enable def and stencil testing, and then in step 2, we render the mirror, or the mirror polygon. That is the polygon we have here. And we render this polygon in order to mask out all the covered pixels in the stencil buffer. And how can we do that? We just clear the stencil buffer initially so that all the values are 0. Now, this is just one call or one initialization step. If we, so to say, create that stencil buffer, we let all the values being set to 0. And then we can again control what kind of operations in the stencil buffer stage, so to say, are carried out. We cannot write a shader program which tells us what to do, but we can control the state of that stencil buffer stage in a similar way we control the state of the def buffer stage. And here in particular we say comparison always, and comparison always means whenever now a fragment is generated when rendering the mirror polygon, No, we always let it go through. No, we don't perform any stencil test. And at the same time, we set stencil operation increment, and this means whenever a fragment survives the depth test, and keep in mind, no depth test is applied here, so all the fragments for that mirror surface survive. And whenever this is going to happen, then at the corresponding location in the stencil buffer, we just increment the stencil value by 1. And it's clear what that means. That means that after this stage B here, once we have rendered the mirror polygon, then if we now look at the stencil values, then wherever a fragment has been created for the mirror polygon, the stencil buffer value will be 1, because we have from 0, we have incremented by 1. And in all other locations in the stencil buffer, the value will be still 0. Yeah, and now what we do is, so now we have created that dissolved pattern. So we have 0 here, and we have then, if we would draw the content of the stencil buffer values here, we would see that they are all 1, meaning that now we have a dissolved pattern here, which is 1 in the interior of that projected mirror polygon and 0 otherwise. And now we can keep on going by saying, okay, now we flip the scene to the other side of the mirror plane, meaning that we multiply the model view matrix with a reflection matrix. And then we render the flipped scene, but we render it only to those pixels where the corresponding stencil buffer values are equal to 1. Because these are the pixels into which, so to say, the mirror plane has been rendered, and only in these pixels we want to see the reflection. And therefore we would say, okay, now we set the reference value of the stencil buffer, we set it to 1, so that now only where the reference value is equal to 1, the fragments survive the depth test. The comparison function is equal, in order to say only when the stencil value which is stored in the dissolved pattern is equal to the specific reference value we have selected, which is 1. And stencil op keep simply means, okay, if that happens, then we just don't do anything with the stencil buffer values. We just leave them as given by the dissolved pattern. And this would then render the flipped scene to only those pixels into which the mirror polygon has been rendered. Yeah, and in addition, that's indicated by the star here, in addition, we clip everything in front of the mirror plane using a clip plane. As I said, you just specify that clip plane here as a shader variable, and then in the fragment shader you can just compare the fragment location against the clip plane and say that you discard all the fragments which are in front of that specific plane. It's a simple shader operation just by using the distance of a given point location to the clip plane. Okay, so, and then what we do is, we reset the model view matrix to its initial state. So now we want to render the initial scene, and now we render the initial scene, but we render the initial scene only where the pixels have not been masked. Because if we now render the initial scene, we want to exclude those parts which are covered by the mirror plane, because in these pixels we have now rendered, so to say, the flipped scene, or to show the reflections, meaning now in the final rendering pass we have to restrict drawing to only the exterior parts which have not been masked by the dissolved pattern at the beginning. Yeah, and therefore we simply have to switch the stencil test by saying now render the initial scene, but only render it to those pixels where the stencil buffer values are equal to 0. Yeah, so then this gives the final result, the mirror rendering algorithm, stages A to F, which we have described. We create the dissolved pattern here by rendering the mirror surface. Then we render the flipped scene only to those locations in the pixel raster which are covered, so to say, by the mirror surface. Then we add the initial scene, which is rendered only to all the other pixels which are not covered by the mirror surface, and then by just adding the pixel values all together, we finally arrive here at the image, which now contains the mirror surface and the accurately reflected seen parts in that surface.